Welcome back. Today we'll be continuing our coverage of DC circuit analysis from the FE Engineering, Electrical, and Magnetism chapter. And we already looked at how to use superposition when we have a little bit more complicated circuits where we might have multiple voltage or current sources. Today we're going to look at another approach to solving those problems, which is Kirchhoff's laws. So here are the steps we're going to follow, outlined one at a time, and we'll move through them as we try to solve this circuit problem. You can see we have two resistors, we have two voltage sources. It's not an incredibly complicated circuit, but you do need some kind of tactic to solve it. So using Kirchhoff's laws, the first thing that we want to do, just to keep everything clear, is label our junctions. So our junctions are going to be these points here, denoted by a dot on my diagram, but they're really points where you get some kind of T in the wiring of the circuit. So something's going to split off. So we can name this top one junction 1, and we can name this bottom one junction 2. And if we trace the wires of our diagram, we see that we don't have any more branching off from the circuit. So those are our two junctions. And we can see I've labeled them here. Next, we're going to want to choose a direction for the current. Now this, just like which junction is junction 1 and which one's junction 2, is an arbitrary choice. So we can choose any current direction we want as long as we choose ones that make sense, and I'll explain that in a minute. And then as we solve the problem, if we get to the final result and our current values end up being negative, well, that just means we probably chose the wrong direction. So if we get a negative value, it means the current actually goes in the opposite direction, but it's not a big deal. The numbers in the problem will come out to be correct either way. So the thing to remember when you assign these is that the directions have to make sense with the node law. So we'll take a look at that in a minute, but for now I'm going to arbitrarily say that we'll call this our first current, I0. We'll call this one our second current, I1. And we'll call this one I2. So we have three currents running through here. Again, you want to split your currents based on your junctions, based on the branching of the circuit. So now that we have our current directions laid out, what we're going to want to do as part of this step is to assign positive and negative values to each of the components that we have here in the circuit. So for our voltage sources, this is pretty simple. This is already predefined. So the longer end of that terminal is always going to be the positive terminal, and the opposite will be the negative. So you can just use that convention. And then for the resistors, what we want to do, and I'll draw it over here, is whichever direction the current's going, we just assume that the current is going to carry a positive charge with it. So we've assigned I0 to go in this direction, right? We don't hit a resistor. And then I2 is going to go through here. So it's going to start at the top of the resistor and flow to the bottom. If it starts at the top, we'll assume that's a positive, and then the bottom will be negative. And that's all we flow through for I2. And then I1, we move through the battery, and then we go again from top to bottom through the 150 ohm resistor. So the top, where it hits first, will be positive, and the bottom will be negative. So now we want to evaluate Kirchhoff's node law, and we'll also, secondary to this, assess if the directions we've chosen for the currents make sense. Most of the time they will, most of the time you can choose arbitrarily, but we just want to verify that. So Kirchhoff's node law essentially says that all of the currents entering and exiting the node, any particular node, or our junctions in this case, should sum to 0, because that electrical energy is conserved. So the current coming into a junction should equal the current going out of a junction. So let's look at junction 1. You could look at either junction. We're going to look at both. Normally you don't have to look at both, but we're just going to do it to assess that everything's correct. So at junction 1, we'll assume anything coming in is a negative current and anything going out is a positive. So we could see all we have coming in is I0. So we have a negative 0 current. And coming out, we have I2 going down here and I1 going down here. So plus I1 plus I2. And we said that the sum of all of these is 0. Now a better way to write this would probably be to move the I0 over. So we'd have I0 is I1 plus I2. And if we look at junction 1, that makes sense. I0 is coming in. It has to be conserved. So I2 and I1, their sum needs to be the same as what I0 is. So this is the node law we'll use. If we take the node law at a different junction, we should get the same result. So we're just going to verify that. You don't have to verify every time, but just for our own knowledge. If we look at J2, we've got I1 and I2 coming in, so negative I1, negative I2. And coming out, we have that I0, and their sum equals 0. And again, we want to move the negative values to the other side of the equation. So again, we end up with I0 equals I1 plus I2. So we can see that there's consistency at all the junctions, which is what we want. So when I said you have to choose directions that make sense, they have to make sense in the sense that all of the junctions should have consistent current equations. This is a fairly simple problem. Most of the ones on the FE exam will look similar to this type of layout. So usually you don't have to do this check. You can arbitrarily choose your directions for your current. But every now and then, there are more complicated problems where you might not be sure if the directions you've chosen are consistent throughout the circuit. So now that we've looked at the node law, we want to look at Kirchhoff's voltage law, or we want to look at the loop law. So here we last evaluated current, now we're going to evaluate voltage. Here we need to choose a loop direction. Again, this is a bit of an arbitrary choice. You don't have to go in the same direction as the currents that you've chosen. I usually tend to do that just to keep everything consistent. But the idea is that every circuit is going to have a number of loops through it, and you're going to choose n-1 loops. So let's look at what that means. So if we look at this circuit, it has this kind of layout. I'm just going to draw a very simple sketch here. It has this kind of layout. And we say, well, how many ways can we loop around the circuit? Well, we can go around this left-hand side and do a loop here. We can go around this right-hand side and do a loop here. And then if we wanted to, we could go around the entire thing and do one big loop. So in this case, in this circuit, n equals 3. There are 3 loops available to us. And we want to choose n-1 loops. So we want to evaluate 2 loops. So in this situation, the 2 loops I normally choose are the 2 internal loops. I think that makes it a little bit easier. If we look at the external loop, it's got 2 voltage sources in it, so it's not helping us any. But if we evaluate these 2 internal loops one at a time, all we have is a voltage source and a resistor. So it gets a lot simpler. So now we have to choose our loop direction. Again, I said it's arbitrary. I'm going to choose to go in the direction of the current. So we'll have one loop going in this direction, and we'll call it loop A, just so we don't get confused. And then I'll have another loop going in this direction with this current, and we'll call it loop B. So now we have our loops diagrammed, and I've blown up our diagram a little bit since we have a lot going on. And now we want to write our loop equations. And to do this, we're going to need some conventions. So let's look at what we have here. So if we have a resistor, and our loop path is entering, and it's going from negative to positive, we're going to say that this is a positive uptick in voltage. And by the same practice, if we have our loop coming in and we have a voltage source, and I'm going to draw it a little bit simpler, and here's our loop, it's coming in, and again, that's going from negative to positive, we'll say that that is also a positive voltage. So now we want to evaluate each loop, and we want to use Ohm's law once again. So V equals I times R. And we're going to evaluate one loop at a time. So let's look at loop A. And we want to pick a consistent starting point just to make it easier on ourselves. So we'll start both at J1. And we're going to follow the loop path. So A is going clockwise around just loop A. So we're going to start at J1 and we're going to move clockwise. And the first thing we're going to hit is this 80 ohm resistor, right? And you could see that the first terminal that it hits on the resistor that we labeled before with the current is positive, and then the second one that it hits is negative. So the loop is going through, it's hitting positive and then negative, so it's the opposite of this. So it's going to be negative I2, which is your current, times 80 ohms, which is your resistance. And remember, we do this because we want only voltage values here. So the voltage is I times R, so the current through that resistor is I2, and the R value is 80 ohms. So now we continue around clockwise, and the next thing we hit is this voltage source. And we could see that we hit the negative terminal first and then the positive, and if we go from negative to positive across a battery, that's positive. So now again, remember, we're only considering voltages, and we have our voltage here. So this is 2 volts. And then we continue back and we hit junction 1 again. So that's everything in this loop. And Kirchhoff's loop law or voltage law states that the sum of the voltages through any loop should equal 0. So that's our first equation for loop A. And now let's evaluate loop B. And we're going to use the same method. We'll start at J1. This is also going clockwise. So if we start at J1 and we trace clockwise, the first thing we're going to hit is the positive on the 9 volt and then the negative. So if we're going from positive to negative across a battery, it's the opposite of what we have here. So it's going to be negative 9 volts. Again, remember that it's voltage. We continue past the battery. The next thing we're going to hit is that 150 ohm resistor. We'll hit the positive terminal first, then the negative terminal. So again, that's a negative. What's the current through there? Well, that current is what we called I1, and the resistance is 150 ohms. So I times R is going to be our voltage. We continue clockwise, we'll hit junction 2, and then the last thing we'll hit is that 80 ohm resistor that both loop 1 and loop 2 share. And again, we're hitting the negative terminal of that resistor first, and then the positive, so this one is actually a positive. The current is I2, and the resistance is 80 ohms. And now we're back to J1, so we could say that the sum there equals 0. So now we'll write out our equations. You could see we have the 3 of them we found already. So the first one we wrote with our node law. The second one we wrote with loop A. And the third one we wrote with loop B. Now I didn't tell you what to solve for in this equation, but we're going to solve for everything, just for good measure, all of our currents and all of our voltages. So our voltage sources, we already know their voltages, so that's good, but we want to find the voltages through the resistors. And if we look here, we could see that we have 3 unknowns out of these 3 equations. We have I0, I1, and I2 that we don't know, and we have 3 equations. So 3 unknowns, 3 equations, we can solve this pretty easily. So let's take a look at our first equation. So if we know that negative I2 times 80 plus 2 equals 0, I'm going to remove some of the units for now, then we could say that 80 I2, I'll just write this a little differently, equals 2. So I2 equals 2 over 80, which equals 0.025 amps. So that's going to be our current for I2. Now we can take our current from I2 and plug in here. So negative 9 minus 150 I1 plus I2 we just evaluated, 0.025 amps, times 80 equals 0. So negative 9 minus 150 I1 plus the sum of the product rather of these is 2 equals 0. So we have negative 9, positive 2, so negative 7 minus 150 I1 equals 0. We can move over that negative 7, so negative 150 I1 equals 7. And I1 is going to equal negative 7 over 150, which is not a nice number, but it's negative 0.046 remainder amps. And note that this is negative, so remember we said if we get a negative value for something, it just means that we chose the wrong direction. So I2 should have been, or rather I1 should have gone counterclockwise, but it doesn't affect the value. So we have our value here. So we have I2, we have I1. We could use our node law now. I0 equals I1 plus I2. And if we sum those, so this will be negative 0.046 remainder plus 0.025, and we'll end up with around negative 0.0216 remainder amps. And you could see yet again that we have a negative value for our total current out of I0, so both I0 and I1 should have been flipped. But again, we have the values there. So now to assess the voltages across each of the resistors, it becomes fairly simple. So if we want the voltage across the 150 ohm resistor, went through I1. So the current there, as we said before, is 0.046 amps. And again, we don't have to worry about the negative here. And the resistance, obviously, was 150 ohms. So if we do that math, we end up with 7 volts. And if we look at the 80 ohm resistor, that was coming through I2. That was the current that flowed through it, so 0.025 amps. And 80 ohms was the resistance. So again, V equals IR. And our total will be 2 volts. So there we have our voltages for our resistors, all of our currents, and we obviously have our battery voltage. So to summarize, we first label our junctions just for consistency. We arbitrarily assign a current direction. We want to make sure that they make sense. And then we want to use that current direction to assign signs to the resistors, and we can assign signs to our voltage sources just based on the layout, the direction of the terminals. We can write the node law. We can check for consistency, but on simpler circuits, we can probably figure it out by eye. And then we'll assign loop directions, again, arbitrarily for our loop law. We'll write the equations for the loop law using V equals IR around each loop. Remember, we want n minus 1 loops. And then we will solve all of the equations simultaneously to get our end result. Enjoying these videos? Follow the links in the description below to find out how you could reach out for personal tutoring. Like and subscribe to get notified when new videos drop, and comment with suggestions for future topics.